Welcome to my talk, gotta go fast, high performance Vue.js, or what to do when it isn't automatically fast. So my name is David. I've been at clickbar for about 8 months now. So this is my first talk, and it's also, I think, our first talk in English, so wish me luck. Why did I choose this topic and this title? Well, our Vue usually is quite performant out of the box, so you don't ever think about performance, but we recently had a project where we had a really complex page, and once it got laggy, it was really hard to optimize. And from optimizing that, we learned a lot about how Vue works and what helps with optimization. So first, quickly, the importance of performance, obviously for fluidity and immersion. If every interaction is snappy and you have 60 FPS, it just feels good to use the software. It's fun and it leads to happier users. And it also leads to more users. If your software is very laggy, people are more likely to bounce and just not use the site again. And it runs on more devices. So as developers, we often develop on these really fast machines in the office, but in reality, it runs on, on tablets and phones. So it's important to be performant. Okay, so to give the rest of the talk more context, we need to make sure to understand the reactivity system in Vue very well. So it's basically made out of 2 parts. So there's this right part, fine-grained part, and the left part, which is coarse-grained. So the right part is basically where all the data happens. So this is your reactive data, this is your computed data, this is all the watchers. And then on the left is the part that renders to the VDOM. Right, so this is based on the data on the right, but it's a bit more coarse-grained, and I will get into this soon. So let me go over a few reactivity mechanics. So let's do fundamentals here. So this is, I'm sure we've all seen this. This just declares a reactive variable. And what we can do is we can do watch effect, and we can log this out. And then when we see what this does, I'm going to go to see this prints Alice. But this doesn't only print Alice, but this also remembers that this effect used name. We can see this if we do this here, right? Very normal. It prints Alice and Bob. And the mechanism behind this is called read-based auto-tracking. So we didn't have to tell it that this depends on name, but it just figured it out because we used name. Alternative to watch effect is just plain watch. So you give it name, and then it gets in the new value, right? And so this will only print Bob because there's only watches for changes. But a very common pattern is to do this immediate true, and then it basically behaves like watch effect did up here, where we get Alice and then we get Bob. So pretty simple. Let's get to fine-grained. So here we have a car, which is a reactive object, and it's also a nested object with this engine object here. So if we add a watch effect and we say console log, this car goes car.engine.range, right? So now we get this. This car goes 370 miles. Now, what I mean with fine-grained reactivity is if we modify this car at all, right? We say year is 2023. This doesn't run the watch effect again because this it doesn't just track the car, but it tracks the range, right? It tracks it all the way deep here. If we say this car made in car.year goes this, then it will say 2 things. Now, but what happens if we overwrite the whole engine? So we say, let's say it's a hydrogen engine, but let's say the range is still 370 miles. So what one might expect is that this doesn't run because, the dependency didn't change. But this will actually run a second time. And it's because, well, the engine as a whole changed, so it doesn't check again. It just knows this changed somewhere, so we have to run this. And here we can demonstrate an interesting difference between watch effect and watch. Because if we do watch instead, and we return car engine range, right, and then we just log this. Right now, well, we need to put immediate true after this. So now, as you can see, it only logs it once, even though we create a new engine. But if we set this to 271 miles, it will log two things. So this is an important difference to remember, that you can use watch to really make sure that if the value itself doesn't change, some other code isn't run. All right. Then let's get to compute it. So we all use compute it to create derived state, which is kept in sync with other state. But it also has a use for caching expensive computations. So for example, here, this implements the binomial coefficient. This is just n choose k. This is a somewhat expensive operation, like it calls factorial, and this is some recursive. So this takes a bit to compute. So what we might do is we say combinations, 7 items, choose 2, and we say computed, choose input. So let's log this out, combinations. And every time choose runs, we log this out. So we know when choose is called. So we log this out, we see computing 7C2 and then 21. If we log this out again, it just logs 21 without computing the thing again. So the value was cached. We can also go input, we can set it to something that it already has and log it, and it also doesn't recompute. Right. So let's replace this with watch effect. We'll just log out combinations. So this basically demonstrates what I just showed you again. Well, this does the same, but let's set input.k to 5. So 7 choose 2 is the same as 7 choose 5. They're both 21. But this computation will obviously run again. It has to figure that out, but it will also cause reactive updates. As you can see, it logged 21 again. And maybe this is not what we expect from computed. We use computed to, put a wall in the update loop, so it stops propagating. But here, it didn't change, but we still got the log. So the way to do this is to do what we did before, right? We do this, and we do this, and we can do immediate true. And now, as you can see, it computes it twice, but it only logs it once because this is not different. And if we change this to 4, then we get a different value. So that's that. Lastly, I want to get a bit into disposal. This is a bit more of a niche topic, but it's important for what we do later. And it's basically all the reactive trackers, they have to get disposed when the component gets unmounted, right? This usually happens automatically, but I'll show. So we have a variable called current time, and this gets set every second to the next current time. And when we unmount the component, we clear the timeout so that the timeout starts. Oh, this should be clear in default. Okay. So if we go watch effect, console log current time value, we see this ticks up once a second, that this does what we want. And if we unmount the component, this will stop logging. But let's say instead we have a button that enables this logging. So we would do something like this, click button. Imagine this is called from somewhere down here. And then this does the same thing. Okay, so we do console log current time value. So the problem with this will work, but this actually leaks memory. So this leaks memory. This watch effect will not be disposed because it wasn't run at the start of the component setup. So in addition to memory leaks, this could just leak behavior. You could have behavior still running even though the component is gone. So how do you do this the right way? So to do this the right way, you see that this here returns this stop handle. So what you really do, you get this handle that it returns, and we want to save this somewhere. So let's say we have handlers, which is watch, stop, just an empty array. And every time we click the button, we also remember the stop handle. And then on unmounted, we go over every handler and we just call it. It's just a function. So this works correctly now. This will do what we want and it will not leak. But it was important that we realized that this would have leaked if we didn't do this. One last thing we can do is we can replace this on unmounted with a more general version, which is called unscope dispose. So this, if you're in a component, this will behave exactly the same. But if you're outside of a component, maybe you're writing library code, this will also work correctly with custom scopes. So in general, it's better to always use this instead of on unmounted because it's more abstract. Okay, so that was the fine-grained reactivity I was talking about. Now to the coarse-grained reactivity. So let's say we have some text and we have a number, right? And we show it here. The P text. And let's say we also have a button which changes the text. So it says click. We do add click. Text is B, right? So this is pretty simple Vue code, and it does what we expect. But the thing is, Vue knows that only text has changed, but it will also update this. It will re-render this P. It will generate this again, and it will diff it. In this case, obviously, this is not a performance problem, but this exemplifies what I mean with that. As soon as you get to the VDOM, the updates are coarse. So imagine that there's a big watch effect around this, and every time anything changes, it re-renders it. But yeah. So now, why is Vue, Vue is still very performant out of the box. So why is that? And I can best show this in the playground. So I gotta stay here. So there's this Vue playground here, and the cool thing is you can look at the output. So Vue, these single file components are compiled, right? And this is the core of Vue performance optimization in the compile step, because it does some static analysis to make the application faster. So this is very simple. It just displays this message here. The first thing it does to optimize it is it uses something called patch flags. So it keeps track of in what ways you can change the element. So this one here, the only thing you could ever change is the text. So the patch flag is 1. Here it says text. If we say this has a class too, right? Let's say this is also message. Then the patch flag becomes 3, which is like 2 and 1 combined in binary. And now it's text and class. So this basically means the differ has to check both the class and the text. So this is one information the compiler gives to the runtime. Then something that's, I think, the most powerful is static hoisting. So let's put some text here, and we can completely spam this, and we can even have some nested hierarchy like this. And what Vue will do, because this has no dependencies, is it will pre-compute this up here, hoisted 1. This will run once on application startup here. And it just puts this in here. So that means all your static divs and stuff you use for CSS and for styling or for layout, it doesn't matter for performance because it just does it once. And then the last feature is that it caches props from comps. So you can see this component here, very simple. It takes a number and it shows this number. So let's use this. Use it like this. We say number is num, right? So what happened now, if we update message, it would go over this comp again. It would generate this object, but then during the diffing, it would find out, hey, the number didn't change. The last time it was 42, now it's 42 still. So that means we can skip the update completely. So this is the very important thing to keep in mind. If the props for a component, for a child doesn't change, then it won't regenerate this child. It will just reuse what it had before. And yeah, this is often where a lot of the performance problems come from, when you have these props which change more than you expect them to change. So yeah, this slide just sums up what I just said. Yeah. So what actually causes poor performance then? So in my experience, it is a combination of lists, prop instability, and large components. So why lists? Well, lists is the only source of work that has to be done that isn't constant. Everything else is constant, but lists, they can scale, right? They can be O(n) or even O(n) squared. So this is where usually performance problems come from. If you don't have lists, then usually you have good performance. Then prop instability is what I just showed. When props change more than you think, they change, but the result is the same. So you didn't really want them to change, but it had to do the whole DOM diffing, and this is where a lot of lag can come from. And then third is large components, which I will talk about later. So example project number 1. So let's go here. I'm going to enable this project. Okay, so this project here. So I have this little lag meter down here, which will show if we're lagging or not. This is going to be spinning the whole talk. So this is a sample application, which is basically, imagine this is for a game developer who's trying to create some items for his game. And each item has a drop chance and some gold value. And basically what he wants to ensure is that items that don't drop a lot are worth a lot, right? And he uses this chart to plot his items and see if it's balanced or if he needs to adjust anything, right? So as you can see, this chart, it works. Let's go into a scatter plot page. So how did he set this up? Or did they set this up? They get the items from the outside. This is just an array of items. All right, pretty simple. So now they have the items. And they use this scatter plot component. Now, this is a generic scatter plot component. This could be from a library, or this could be some project-wide thing that's used everywhere. You don't know. But the scatter plot doesn't want gameplay items, but it wants points. So what the user has to do is they first have to map all the items to points, right? So they create this points thing. They just say you computed items map, and they create these points. They say the X position is the drop chance, Y position is gold value, etc. Right, exactly. And when a point is selected, this scatter plot throws up click point with the ID of the point that was clicked, and then the item here gets selected. So if we use this, we see we can click this, the selection works, but it's a bit laggy already. If we start to move this though, you can see that it's really lagging. So this is not really good to use, not really fun to use. This is a bit faked. Let me get into this. There is, so usually the thing that causes lag is like large components where each update takes a long time, and then you do this n times. Imagine in a full scatter plot, each of these points would have like a huge pop-up with tons of DOM nodes. It would have maybe a shadow. It would have some lines going through it. So it would have a lot. Obviously, I didn't do it for this small example. So there's this synthetic lag basically built in. So this here is an expensive component. This could be anything. And this takes 500 microseconds to render. So this is a really short time. If you only update one point, this doesn't do anything. But if you update the whole list, then it starts lagging and it looks like this. So how do we know where it's lagging? What you can do is there are these Vue dev tools you can get, and they have this performance chart. And if we start doing things, you can see, hopefully, yeah, here, it's creating these entries here. And see, okay, the whole scatter plot updates, and then it's made up of a whole lot of scatter plot points, all of these here. So this tells you where you have to look. There's also some hooks you can use. That, for example, on render triggered, you can put this in a component, and it will tell you what variable changed. So you can know better where the change is coming from. Okay, it lags even more with the DevTools open, so I have to close and open them again. So, so how do we go about this, right? This is not a good UX. So I'm just going to plot page. So let's assume that we have no control about scatterplot. Maybe this is from a library, right? We can't do anything, or it's used so much that we don't want to change the API. So what can we do from the outside? So the problem is that every time anything changes, like any item changes, the whole array gets recomputed, right? So we move one thing and it recomputes 300 things. So we want to basically reuse objects. This is our goal, right? This is what we want to try to do. So let's try to do this. Let's do points better, right? And let's start out just with a normal computed. So we do items map. We get each item like this. So what we did up here is we basically did this, right? But this is not what we want, right? This will create a new object every time anything changes. So this will cause prop instability. So what could we do instead? Maybe we could we generate an object up here, and let's make it empty first and say this is a data point. And we return this df. And now we just want to keep this object in sync without destroying it. So we could use a watch effect. We say watch effect, and then we do object assign, which just copies all properties from one object onto the other. So we say object is the target, and the source is this thing, right? So the idea here is we hope that the object is created only once, and then it gets updated by this watch effect. So let's start this out. And all right, so it looks the same, but as we click on it, oh no, I'm sorry, it still works. We need to use points there. So as we click on it, it's performant now, but it doesn't work anymore. So what is the issue? The issue here is this is a plain object, so it has no reactivity tracking. So the solution is quite simple. We do this. So let's click this, and as you can see, with this change, the whole thing is now buttery smooth. With one exception, if we create items, we can see it still lags. So for every item we create, it causes a new lag spike. So why is this? This is because when we press create item, we actually update this items array. So this whole map will run again. It will create new objects. It will do what we didn't want to do. So we want to cache objects we created before. So let's try this. So we say we have a cache. We have some key, let's say it's just a number and the data point. And what we want to do here is we want to say if we already have the thing, right? Where in our case, the index is the ID, then we just return, we do return cache get of index, right? And then down here, when we return, we say cache dot set index object. Right. Let's try this again. So this should still work. And if we press create item, this doesn't lag at all anymore. So this is almost complete. Remember what I told earlier, this will leak some memory. So what you got to do is you get this, you keep a array of these handlers, right? You add the thing to the thing, and then we do on scope dispose. So this will run when the component is removed, unmounted, and we just go over each handler and call it like this. Okay, so this is complete now. This works. This will not leak memory. This is performant in if you change an item, if you add items. It also works if you delete items. So we managed to make it performant from the outside. But problem is, this is kind of a lot of code to write every time instead of this. One thing we could do, we could generalize this. This is a generalized version of this. We'll not explain this in detail, but it's basically a generic version. You pass in the array, you pass in the map function, you pass in the key getter, and it just it does what I just showed. I can show how this is used. So we can go points best. This is optimized map. It doesn't know that it exists. Optimized map. All right, let's see. Optimized map. Where is it not? It's not. All right. Let's just use it without it being there. Optimized map, it takes in the, actually, maybe we can import this ourselves. Right, let's reload. Let's see if we can import it. Here we go. Quick fix. Okay, so taking the items, then each item simply maps to this here, what we wrote before, nothing new. And to get we need to give it this key thing so it knows which object is already in the cache. So this was just our index. So we just do this, right? So this is pretty short, and I'll pass it in here, and this works as before, right? Okay, so this is a cool pattern, but the problem with this is that it basically expects the user to optimize everything from the outside. What we would really want is we want the scatter plot to be fast, so that it doesn't matter how you use it, it's fast anyway. So let's try that. We're gonna undo what we just did. So okay, so this is where we started. Okay, so what we can do, the problem is we do this map at the top level, right? Every time anything changes, we map every item anew. What would be cool is if each point would map the item themselves. That means the map would be at the lowest possible level, and we would not affect a lot of elements. So what we can do is we say, let's make this generic. So let's say this takes in a generic. And instead of points, we just say you give it any data, right? So this is just a T array. So we can give it our gameplay items directly, and we also give it a map. So let's say to point, which is just this is the singular for data. I think also sounds weird, but I'm going to use this, which returns a data point, right? So this map. So what do we do here? Here, let's just say datum I in data. For this time, let's temporarily use the I as the index. You usually shouldn't do this. And then instead of point, we just say data, right? We give it that, and we also give it the 2-point mapping function. What we can also change is this emit. We don't click a point anymore. We click any item we have. So we change it to this. And this datum is just a T directly. So right, say click datum, and we just put in the data directly. So let's go into the point. So the point now needs this generic too. Doesn't get a point anymore. It gets this, and it gets the mapper, right? Like this data point. Okay, now we see point is undefined, but point, it's really easy to define point. We just say point is computed, which is props to point, props to point, props data. Okay, right. So what we're doing here is we're executing the map like before, but we're executing it as low as possible, so that when something changes, we don't update much of the tree. Let's see here. Okay, so this doesn't take points anymore. So this takes, we just say data. And here's the cool thing, we can just pass in our items, right? We want to map our gameplay items, so we give it the items. I think that's quite nice. We still need to give it the mapper. So let's say function to point. This takes an item, right? And this will just return this here. So okay, we made the map. This is the same map we had before. We say to point, and now this is click datum, right? And then select item. This is also good. It just gets the item, right? If you just give the item back, we don't need to search for it. We can just do this. Let's hope this worked. So we click on this, and it is smooth again, right? And we didn't have to change the way we call it from the outside much. Only issue you can see is when you click these, it lags for every selection, right? That's what it lags for. And why does it do this? Well, remember in the map here, we use selected item, right? That means every point depends on this. That means when we change the selected item, every map will run and we will update 300 things. So the way we could fix this is we take this out, and in the scatter plot, we pass in the selected thing. So we say selected, this is T or undefined. And then in here, we just tell it if it's selected or not. So we say the item is selected, right? We go here, this just gets selected Boolean. And then we just use it like that. And here we pass it selected is selected item. Let's see if it works. Okay, so we can select things. It doesn't lag. Beautiful. Okay, so this is one way we can do it. So we changed our API completely to be generic, but the benefit here is we can just pass in the items. And I think it also feels good to use, not to have to do the map at the top level. Okay, so I'm going to get to the simpler solution now. Scatter plot to replace all these. Scatter plot point fresh. Okay, let's see. So this should be back to the bad. Yeah, okay. So we're back to square one. Now I'm going to introduce a new tool, which is a very much a power tool, which is vmemo. So vmemo, it takes an array and basically it recomputes a subtree of the template only if the array has changed. And it not only skips the diff, but it also skips the VDOM generation. So it completely stops a part of the generation. And this is really a magic tool for optimizing most things if you use it right. And I'm going to show you just how easy it makes things. So, well, what do? We go into scatter plot, and this was a problem here, right? So let's just put vmemo is empty array. Let's see what this does. So we go here. And so you can select, and we're at it's performant again, but it doesn't do anything. And the reason it doesn't do anything is because it has nothing that changes, right? This means no dependencies. This means it renders once. We could also write once. This does the same thing. This is a synonym. So, okay, what do we want to listen to? Let's say the position, right? So we put in point X, point Y, right? So when this changes, we want to update the thing. So we click this, move this around, and it's already smooth. Only problem is when we click this, as you can see, it doesn't update the selection ring. So we go like, oh crap, we forgot point got selected in here. Now we go here, and now this is smooth, right? The clicking stuff is smooth, creating new items is smooth. This is all it took to make the component not lag. Only you can see the problem is you can forget to put in dependencies here. For example, I mean, we could put in X width and Y width. We might forget these. A little hack you can do is you can just put in everything point has. So you just say object values of point. So you don't need to think about what point has. You just put in everything. And this is good because point is an object, but the values of points are just primitives, right? So this is why the comparison will still work. Now we have everything in there. If we add properties to point, this will keep working. So, conclusions for the scatter plot. So this showed map data. And a big problem is if you create new objects, this will cause prob instability. So if you can't change the thing you're mapping for, if you're on the outside, then your best bet is to try and reuse objects, try to cache things you already used, and try to change only the object that you changed. But there isn't a standard way to do this, really. If you have control over the inside, either try to move the map to the bottom of the tree, like I did with the generic, or you memoize, right? You put at the spots that take the performance, you put a vmemo, and you just hope to include everything. Okay, so example number 2, this will show large components and why they can be laggy. Let me do this with app. Rep 1. Okay, so this is the component. So this has an expensive part and an inexpensive part. The expensive part is this. You click this here, and this computation, which is just ×2, but imagine this takes a very long time. And this is representative for a component that has like a lot of, like maybe 300 lines of code, 200 lines of code, right? So every update has to generate a lot. This is just a symbol for this, right? And now this text here, if we start typing, it looks like this. This is not very fun to use, but this is a bit strange because if we go into the laggy here, you can see this only depends on text, right? So we only change the text. We only want this P to update, but it recomputes the expensive part, right? And this is the coarse grain thing I meant, right? Vue doesn't know that, well, Vue does know that it changed only text, but the way it's constructed right now means that it has to re-render the whole thing. So yeah, again, this year, instead of expensive operation, right, a solution for this, you put this in a computer, it would be fixed. But imagine this is just a large part that goes, like, just a huge component. So what can we do to fix this? So one solution is to use this prop boundary thing I talked about earlier. So let's take this part here and replace it with the incrementer, which I made here, right? So incrementer takes in a number. This uses the new define model syntax. This is just from Vue 3.3. This is just syntactic sugar for model value and the emit, right? And this is the whole thing that we just did, but it's in a component. So we're now here, we go here and we make this dependent. So let's say number is number, right? What else does it want? All right. Oh no, this needs the V model. This is right. Okay, so we try this out, and now typing is smooth again, right? And clicking this is as laggy as it was before. But so this is one solution. So we use this prop boundary to gain performance, right? It still does the same thing, but we use this to gain performance. Alternatively, we can do the opposite. You can extract out the cheap parts. So we take this part here, right, and we say this is the what I call it just text input. Text input. And this has completely self-contained state, very simple component. Right. And we run this again. This here is smooth, and this is laggy. So this was the same thing. So you can either take the cheap parts, put them in their own component, or you take the expensive parts, put them in their own component. Both ways work. Next, is this the version? Okay. Oh, we reset this. So next, we use our best friend again, vmemo. So with vmemo, what we can do is we see this is the expensive part. We do vmemo. This only depends on number. So that's all we do. This is smooth, and this is laggy, right? So that's vmemo solved this all for us. Now, in this case, it's a bit harder because if this is a big component, like part of the component, it might depend on a lot of props. It might inject some state. It might use some global state manager. So you have to list out all of this in the vmemo, right? And this can be a burden, and this can also be like it can rot once you change the rest of the code. It's hard to keep this in sync. So the real question is, if Vue already knows what changed, right? Vue knows the text changed. So why do we have to do these hacks to make sure it doesn't change more? And this brings me back to the slides. And to vapor mode. So vapor mode is something the Vue team is working on right now, and this is caused by Solid getting so much traction, right? Solid uses these super fine-grained updates and signals, and this is what they're basically trying to emulate. So what it does is it basically does fine-grained reactivity everywhere, and it ditches the VDOM as well. So if you look at this, this is from a talk by Evan Yu. It takes, this is the input, right? Just a button with a click. And this is what it compiles to in vapor mode. So what this does is it doesn't create a component, but it's just a function, right? Which creates some HTML, gets the button from it. And then it just says, this is basically watch effect. And then it just sets the text of the button to count value, right? This is just a simple watch effect. And then it sets up the listener saying, if you click the button, change the count. And then it just returns the diff. It doesn't return a VDOM node. It just returns a plain old DOM diff. And this is way more performant because when you click the button, this changes, then this watch effect runs, and it just directly changes the DOM text. All right, so, and this is expected to come out in Q3, Q4, but this is actually quite easy to implement yourself as an example. So I want to show you how it will look like. So let's go back to this. So let's keep this here, and we want to we basically want to create this, what this creates with the VDOM, what we want to make this ourselves. So let's say create component. So we need to start by making the HTML. So there's this function template that I made. This just takes in some HTML and returns all the HTML nodes. So we put in this, right? We put in all this, and then we can figure this out. Okay, now we need to remove all the Vue specific stuff. Here we have some text interpolation. We need to replace this with a span, so we can access just this. We go span like this. The vmemo, this is not useful anymore. This is text interpolation, don't need this. And we have this listener, also don't need this. So this is the plain HTML we have, right? So we say we get these as nodes. Okay. If you want to know what template does, this is, it just does, it creates a div, sets the inner HTML and returns children. So the what do we do? So now we need to get the individual part DOM nodes to do something. So let's get the input. So this is just node 0. We get the text display. This is the second one, right? This is this P, and then the first child. Obviously, remember, this is what the compiler would create. So this is never something you have to write yourself. Then we get the number display. So this is nodes 2, children 0. This will get this span here. We don't need this is the divider. Then we have the expensive display, right, which is this here. So this is nodes 4. And then we have the button, which is nodes 5. Okay, so now we have these. Let's do HTML input element. So now we need our state. So for our state, we just take the Vue stuff like we had before. We don't need to change anything. So this is where we use Vue again, because the fine-grained reactivity also already works in Vue, right? And now we want to establish some sort of syncing logic. So let's say on the input element, we add an event listener, where we say on input, right? On input, this text here gets changed to input dot value, right? So every time we press a button, it overrides this with the current thing. Also, what we do is when we press the button, so add event listener, when we click the button, then we say, what was this again? The number, yeah, we increment the number, right? So this is all we do. And now we need to add in the stuff that keeps it synced. So how do we keep these here synced with our state? We just use watch effect. So we say watch effect. We say text display dot text content is just whatever is in the text. We can say watch effect number display text content is whatever is in the number, like this. We need to do toString, and we do watch effect. And this is the expensive part, right? We say expensive display text content, and this is this. So we just do expensive operation of the number and then toString. So this is basically what the compiler would generate. So now we just need to return some node from this. So we say, let's say just node. This there's this great document fragment. So this is a document fragment is just a collection of HTML nodes that you can append at once. So we say node.append, put in all the nodes, right? And then we return the node. Okay, so this creates the recap. We create the HTML once, we get the stuff, the nodes, set up the state, set up listeners, we set up watch effect, and when we return all of it in a bundle. And this is the only time this function runs. Right. So let's get it. Let's say component is create component. We're calling it at the root level, so the watch effects get disposed automatically. And now we have a document fragment here, right? So how do we get this into the template? The only way I know so far is you have some sort of hook element. So you do a div, and we call this no, it's not class. It is ref. Let's say container. So we go here. We do container is the ref of this. Right, and then on mounted. So when the component was created, we do container dot value dot append component. Okay, so when we create the component, when the div here is created, we just add the component to the DOM manually. So let's hope this works. Okay, so we have something here. We can type, and it keeps this in sync, and we can click this, and it does what it did before. And all of this is without VDOM at all, right? This is just plain DOM. This is what we wrote so far. The template is only this. And yeah, we didn't have to tell it that this text update is separate from the number update. It just does this automatically. And yeah, so this is basically what Vapor Mode will do, and this will come out like by the end of this year. So I'm really excited for this because it's going to make a lot of things just automatically more performant. So to conclude on the large expensive components. So what you can do is you can extract out the expensive parts, like I did at the start. You can also extract out the cheap parts. So both of that works. Then you can wrap expensive parts with vmemo, but you need to really be careful that you have everything in the list, right? Because otherwise the DOM doesn't update. Or you just wait for Vapor Mode and then enable it when it comes out. And this will make our lives much easier. Okay, so conclusion of everything. So in general, the performance of Vue is often very sufficient. You don't need to think about it, but it's important to know how it works so you can optimize it. My advice would be you just try to use vmemo as the first tool to fix everything. In most cases, it will work well, but you need to be aware that you need to be very careful of how you use it. If you have a large component, split off the expensive parts into small components. This is a way to avoid vmemo, and it makes it faster. And most importantly, keep using Vue because it's only going to get better. Yeah, thank you for listening.